Swayam Prabha. Digital India. Educated India.
In our earlier couple of classes, we have discussed in details various crystal structures which are available in different kind of solids, ceramic materials and others. Those are some of the ideal things one can expect, ideal atomic arrangement, the structure of the different solids. Many different solids crystallizes in different kind of structures with different geometry. However, today we are going to discuss some of the deviations from such ideal structures. Of course, these deviations are at the time being it is restricted to some of the lattice points, and these lattice points may be to some extent displaced or may not be there. Some of the lattice points, particular ions may not be there in the right place. So, these are called the defects, defects in crystals or defects in crystalline solids. There are different category of defects. Today primarily we will be discussing about what we called the point defects. Point defects means these defects are basically restricted to lattice points. They are kind of 0 dimensional defects. So, they are primarily restricted to the lattice, either individual one lattice points or couple of different types of lattice points. So, that is what we are going to discuss today. The defects, and these defects are really called point defects because they are restricted to points, lattice points. Now, in this diagram, it is a little complicated diagram, little busy diagram, but very simple in a sense once we know the principle. Basically, we have a lattice, a oxide, MO type oxides, a metal oxide, a divalent metal oxide. M is divalent, oxygen is anyway divalent. So, we have a array of such divalent ions, alternate ions of metals and oxygen, which is basically a cubic arrangement kind, and in these lattice points there may be different kind of distortions or deviations. We have listed quite a few of them here. For example, this is basically the lattice MO, alternate sides of, ideally alternate sides of metal and oxygen are there in any direction. The first one is what we call the oxygen vacancy. Vacancy is nothing but a missing lattice or missing lattice point, and in the oxygen sublattice. So, this is the missing oxygen. So, ideally there should have been an oxygen ion, but for some reason or other that oxygen is missing, and therefore, that defect is designated as oxygen vacancy. Similarly, correspondingly we have metal vacancy when a particular metal ion is missing. Where exactly it has gone is not of our concern, but when we are looking at this particular area of the lattice, we are seeing that that particular metal ion is not available or is missing from that particular site. So, in addition to the vacancies, we can have interstitials. That means, for example, this is an oxygen interstitial. Oxygen ion should not have been there, but an additional oxygen ion has been introduced in between the normal lattice sites. So, this is an extra oxygen ion in an abnormal site, and it is interstitial position between the normal lattice points, and that is why it is called an oxygen interstitial. So, this is an oxygen interstitial point defect, oxygen interstitial. Similarly, you can have a metal interstitial. So, just like oxygen, you have a metal in an abnormal site which is not supposed to be occupied by metal, but the interstitial site is being occupied by metal. So, it is the position is not a regular position, and therefore, it is a defect, and defect so far as the crystal lattice is concerned. We can have impurity ion. It can form some impurity, very minute quantity of impurity may be added, or either intentionally added or accidentally it is there. So, that here of course, the impurity can go both into the interstitial site as well as substitutional site, because we know about solid solutions where both substitutional and interstitial solid solutions are possible, but in this particular case we have just considered a substitutional solid solution. And so, the L is an foreign atom or foreign ion, metal ion, which has substituted the original metal M2 plus. Now, here it has been written as X plus. Now, it not necessarily this foreign atom can have the same valency as that of the original metal M2 plus. Instead of 2 plus, it may be less than 2, it may be more than 2, and that is the reason I have written there as Lx plus. Okay. So, normally if a different atom of a different valency is there, we call it a aliovalent substitution. So, that is the terminology, but for our purpose it is only an impurity ion. So, that is also a defect in that crystal. In addition, you can have 3 different kind of pairs of defects. These are all single defects, either in the oxygen sublattice or in the metal, either the metal interstitial or metal vacancy, oxygen interstitial or oxygen vacancy. Now, we are talking about not a single defect, but a pair of defects. The very first one is here in the middle. It is called Schottky pair, where both oxygen is missing as well as metal is missing. So, they are forming as a pair together. Earlier we have talked about single point defects or singular point defects. Here is a pair of point defects, they come together, and that is how we call it a Schottky pair. So, it is a metal vacancy and oxygen vacancy, both the sublattice has vacancies in them, and they come closer to each other. In fact, they move also. If they want to move in the lattice, they normally move in pairs. Then we have another type of defect called Frenkel pair. Frenkel pair is primarily in the metal sublattice. So, there is a metal vacancy and metal interstitial. Okay. So, this is a metal vacancy and that is a metal interstitial. Okay. That is one is the metal interstitial, just like earlier we have considered interstitial. So, but only difference here is they are coming in pairs, both of them have been formed together and they will form in equal numbers. So, that is called Frenkel pair, and the last one is called the anti-Frenkel pair. Anti-Frenkel pair is nothing but here it is in the metal involving the metal ions, metal vacancy and metal interstitial, whereas anti-Frankel pair means oxygen interstitial and oxygen vacancy. Of course, this is not that common, but even then it is possible, and there are cases or there are situations when anti-Frankel pair is also available in the solids. So, these are the different kind of possible point defects which can occur in some of the ideal crystals of any type, whether it is a high temperature material or a low temperature material, it does not matter. These kind of things do occur all the time. It is in fact thermodynamically, it is a stable situation to have defects in solids. None of the no solid is actually perfect, all solids will have some kind of defects all the time, and they have a very important role to play so far as the property of the materials are concerned. Just like the crystal structure has an important role, the defects of the crystalline defect also have a very important role to account for different properties. All these defects are normally denoted by some notations, okay, and these are standard notations. Throughout this discussion we will be using them. So, let us have a look at these notations. These are like this: cation vacancy, this is denoted by Vm, that is vacancy, subscript is the site. So, Vm is the notation for the cation vacancy. So, any vacancy actually is denoted by V. So, either it is Vm or the next one, the anion vacancy is Vx. Okay. So, it is the Vx and Vm. Cation interstitial, now in case of cation interstitial it is not Im, and with analogy to vacancy it is not interstitial Im, but it is Mi, it is the reverse. So, it is the interstitial I at the metal site. So, that is how it is Mi and not Im. Anion interstitial is Xi, same as that of or analogous to Mi, the anion interstitial is Xi. Substituted cation, that is basically we have talked about the substitution solid solution. Of course, the notation has been used differently here. There the atom was L, but here it has been taken as A. So, A goes to the M site. In fact, as per the earlier diagram it should have been written as Lm, but for some reason it has been written as Am. Okay. Substituted anion, if it is anion is getting substituted, just like metal is getting substituted. So, A goes and sits the M site, that is why Am. If B goes to the X site, that is the oxygen site, it will be Bx. Interstitial foreign cation, that has not been considered in the earlier diagram, but just like a substitutional foreign atom cation, foreign cation, a interstitial foreign cation can also come in principle, that is Ai. Interstitial foreign anion is Bi, and then we have Schottky pair, it is a pair of vacancies. So, it is Vm and Vx. Frankel pair, it is reverse, it is different, not all, both of them are vacancies, one is vacancy, another is interstitial, and both involving M or the metal, and that is why it is Vm, metal vacancy, and metal interstitial, that is Frankel pair, and anti-Frankel pair similarly in the X or oxygen sublattice. In fact, there has been little bit mismatch between this and the diagram. X we have not considered there X actually oxygen here, okay, and M of course remains as M, and A instead of L we have used A here. So, anti-Frankel pair is Vx, or we can call it Vo, and XOI. X is actually oxygen here. Okay. So, that is those are the notations used for different kind of point defects we have discussed just now, and these notations will be quite important and useful for our later discussion. Then we have since we are talking about ionic solids, oxide. So, we have ions, these are not metals. Okay. The metals also do have similar kind of situations, only thing they do not have a charged species, they are neutral species. So, their things are slightly different, but when we are talking about ionic species or ionic solids, we are considering two different ions, and therefore, we have to we have a situation when they can be either charged or neutral. So, just like the metal can be or metal ions are charged ions, or oxygen ion is a charged ion, other normal metal a metal atom is not a charged one. So, similarly a defect in this case, since we are talking about a ionic lattice. So, there is a possibility of what we call the charge defects or neutral defects. What is the concept? Here we are talking about an oxygen vacancy. Once again, this is the lattice, and here a oxygen was supposed to be there, and the oxygen has been removed. So, it has created the oxygen vacancy, but the question is whether it is a neutral oxygen vacancy or a charged oxygen vacancy, and what is the difference so far as the charge distribution is concerned. Now, the oxygen and its charge, there are two parameters or two components. One is the mass component, another the charge component. So, when oxygen is removed from this, it is no longer there in that site. So, the mass has been removed, but the charge may not have been removed. In fact, the oxygen, when oxygen comes out of the lattice, it will come out in the form of an atom, it will not come out in the form of an ion. Only within the lattice it will have a charge component. So, when it is coming out of the lattice, then it may release the 2 electrons associated with it at the site where it was originally sitting or it was supposed to be there. So, this is the 2 charges, 2 electronic charges which has been left behind when the oxygen has come out in the form of an atom, okay, because the charge, it cannot take charge and come out on its surface or in the atmosphere. So, when these 2 charges are left behind at that particular site where this ion was supposed to be there, then this vacancy is a neutral defect, means it has not disturbed, it has changed the mass distribution. The mass is not there, but the charge is still there. Okay. So, it was 2 plus 2 minus originally, still it is 2 minus. So, in that particular site 2 electrons are floating, and if that 2 floating electrons are sitting in that place, then the vacancy that is created is called neutral defect. Then this is the situation when it is charge defect. This 2 electrons are no longer there, 2 electrons has gone away or shifted away from this particular site, but it may be within the solid. It has not left the solid, it has not left the crystal, but it has left that particular site. So, when that particular site is no longer having that two negative charges, it is absolutely vacant, then the charge distribution has changed, and at that point this vacancy, this particular vacancy now will be called a charge defect, having a two dots means an effective positive charge, a deficient of two negative charges. It was having two negative charges, oxygen ion in the form of an oxygen ion, it was having two negative charges, that negative charge has left that particular site. So, so far as this site is concerned, this is effectively positively charged, double positive charge, and that positive, since it is not the actual charge, it is really not 2 plus, it is the deficiency, just like holes in case of semiconductor physics. This is effective positive charges, and that is why it is not written as plus, it is actually written in the form of a dots. That is the convention used by crystal chemistry or defect chemistry. But what happens, these two electronic charges, two electrons were there, two electrons has been released to the system. So, these electrons has not left the site, left the solid. So, it is there within the solid, but may not be exactly in the same location. So, this what has happened, it has donated one electron to this metal ion and another maybe to another metal ion, that is most likely. Not normally two electrons goes to the same metal site, that depends of course what is the variable valency it has. So, as consequent to that, this has released two electrons to the system, and when it adds to the M2 plus, the M becomes M plus 1, instead of plus 2 it has become plus 1, because one negative charges have been added and that particular metal is capable of changing its valency from plus 2 to plus 1. So, if that is the situation, then this kind of charged and neutral defects do occur. So, one of the condition is the metal present here must have the variable valency, and it must be able to accept this electron. So, otherwise that electron will be hovering around, and it may be energetically less favorable. So, what happens, the charge, this also becomes a charge defect, this is a charge defect, and consequently this is also a charge defect. Okay. It is a defect in the sense it is no longer M2 plus, it is M plus, okay, and this is also M plus. So, this is another kind of defect which has been created by M at the M site, but not its regular charge, it has one less positive charge, which is supposed to be 2 plus, now it has only 1 plus. So, they had a deficient on one positive charge. So, effectively it is a negatively charged species now. So, in respect of the original lattice. So, it has created two different kind of charge, M at the M site with one negative charge here and another negative charge there. So, the reaction is like this, or the changeover is like this. M at M site means M at M site, okay. M subscript M means M at M site, which means two double charges or divalent, that is the normal, that is the regular, and that is neutral, and to that one electron has been added from released by the oxygen or creation of the vacancy. So, creation of oxygen vacancy has released two electrons, and these two electrons have been accepted by two different cations present original lattice, and they have changed their valency from 2 plus to 1 plus, and that can be written that M at M site with one less positive charge, since less positive charge can also be written as negative charge, effective negative charge. So, the effective negative charge here is actually prime, effective positive charge is denoted by dots, whereas effective negative charge is denoted by prime. That is also another convention used in the defect chemistry. In the same manner, it can be the other way also, a vacancy, metal vacancy, neutral vacancy, this is a neutral vacancy, and it has left behind here two holes. Okay. From the concept of semiconductor physics, we have electrons and holes. Basically, holes are nothing but the deficiency of electron. So, here H means a hole is positively charged hole is the deficiency of electron. So, two holes have been left behind, that means two positive charges, and the neutral vacancy has been created. Exactly in the same manner, these two holes have now gone back to two different metals. Okay. So, once that hole is now no longer there at that particular site, the charge distribution has been changed. So, this has become effectively negatively charged place, and this is a place where a metal was supposed to be there. So, it is created a oxygen metal vacancy with a 2 double prime, the 2 or the double prime, which means a effective negative charge, prime means effective negative charge. So, this is effectively a negative charge species has been created here, and consequently to maintain the charge neutrality, two holes have been added to the metal. Now, all these things it is not getting added to oxygen, it cannot, because oxygen has a very stable divalent configuration. So, oxygen cannot be 1 plus or 3 1 minus or 3 minus. On the other hand, metal can be can change their variable valence, can change their valency, and only when such thing happens, then the creation of these defects becomes easier. If metal cannot change its valency, then the vacancy creation is become less energetically feasible. So, it may not form the vacancy or may not form the particular defect. So, once again here it is the reverse is happening here, M2 plus is now changing to M3 plus. Again there should be a possibility that the particular metal can change their change its valency from 2 plus to 3 plus. So, if that happens, then you have again a charge defect, but of a different nature, M not prime, but M dot, that means an extra positive charge has been added here. Earlier an extra negative charge was added. So, the valency was decreasing, here the valency has increased, and by adding an extra hole, and the reaction is written here plus H is dot, which is again effectively positive charge. So, since we are talking about neutral defect and charge defects, so there is a possibility of ionization. So, that is what really happens. There are 4 situations we have discussed, and all these things, no, we have discussed actually 2 different situations, but in the earlier diagram we are talking about either you see either 2 negative charges, effective negative charges, or 2 positive charges, which was earlier in the oxygen vacancy. Oxygen vacancy was 2 positive charges, 2 effective positive charges, whereas here 2 negative charges. Now, it does not necessarily mean that all the time it will be doubly charged, or it may get doubly charged through a stepwise process, and that is what is written here. Initially M at M site will change over to M prime, these belongs to the lower one, and a H dot is created, and this ionization is there be some ionization energy is involved, it may be E1. So, instead of getting ionized simultaneously to both of them simultaneously, it can go step by step manner one after the other. So, that is what has been shown there, that ionization can take place in a stepwise fashion, and so each involves certain amount of energy, and that is what for this reaction the ionization energy is this one, and for the next one or next step E2, and the overall this is the summation of these two, and the overall energy is E1 plus E2. Same way for the metal interstitial, you can have this kind of ionization, and it may be E3 and E4. So, by adding together one metal goes ionization double dot and plus 2 electrons. So, it releases 2 electrons, and the total energy involved is E3 plus E4. Same thing happens with the oxygen also. So, that was your metal sublattice, and here the oxygen sublattice. The oxygen defects can also get ionized in this manner, either they will release some electron or holes. If you can go through these things, it is quite clear. So, instead of as I said, the ionization, both the ionization taking place simultaneously, it will take place normally, it will take one after the other, and each one of them will involve certain amount of energy, either release of energy or acceptance of the energy. Now, with this we come to another concept, this is actually the consequence of defects, non-stoichiometry and point defects. So, there is a strong correlationship between non-stoichiometry and the point defects. What do we really mean by non-stoichiometry? Basically, non-stoichiometry means deviation from the law of constant proportion. For all compounds, ionic compounds in particular, there is always a definite ratio in which the metal and the oxygen are bonded together. So, that is normally not deviated, but whenever there are defects, that deviation do take place. All chemical compounds as a rule follow a definite but simple ratio of the number of atoms in a molecule, as for example, MO, M2O3, MO, MO2, etc. That means metal to oxygen ratio is a simple integral multiple or a factor. So, either it is 1:1, 2:3 or 1:2, etc., etc., right. So, when that is deviated, that is what we call the non-stoichiometry. Instead of 1:1, it may be slightly some fraction of 1, and that means that there is some defects in it, and that because of the defect the ratio has been changed. Deviation from this ratio leads to non-stoichiometry, and molecular formula needs to be written as Mx. M instead of Mo 1:1, it has to be written as Mx, which means that actually denotes what is the exact ratio between the cation and the anion. It need not be an integer all the time, and the result is, of course, the reason for this is basically the point defects, because the point defects, when it is present, if it is present in one particular sublattice, either in oxygen or the metal, obviously it will disturb the ratio until unless there are pairs formation, that means Schottky pairs or Frenkel pairs or anti-Frenkel pairs. If they form in pairs, then of course this ratio will not get changed, and that is the reason these pair kind of defects are known as stoichiometric defects. The others, singular defects, are called the non-stoichiometric defects, and there is because they cause non-stoichiometry or they result in non-stoichiometry of the compounds. Non-stoichiometry is prevalent in several oxides, particularly for those metals with variable valency. As you have mentioned, whenever there is a ionization of the defects, you need a variable valency metal to be present there. So, variable valency metals or the oxides thereof do have a tendency to become non-stoichiometric. Now, these are some examples what kind of non-stoichiometry one can expect in different oxides, and as you can see all the oxides here basically they are transition metal oxides in that series, because they have the variable number of d electrons and incomplete d cell, and that is why the ionization is easier. So, therefore, they have a variable valency as well. Iron oxide FeO, you can see although it is the formula is 1:1, actually it is not 1:1. If you take X, FeOX, okay, FeOX, the X value changes from the minimum value of 1.045 to 1.2. That means the amount of X is much larger than 1. Okay. Normally it should be, as per the formula, it should have been 1, but actual practice it may vary. It may vary from 0.45 to 0.2, which is a quite a large deviation. So, all the time it is more than 1, which means X is more than 1, that means oxygen is more than 1. So, iron or the metal is less than 1. So, metal is actually a metal deficient oxide. It is called the metal deficient oxide because oxygen is more, or sometimes it is also referred to as oxygen excess oxide. So, most of these, some of these transition metal oxides, either metal excess or metal deficient oxides normally they form. Nickel oxide, it is sometime it is 1, but many a time it is more than 1, but the deviation is little less. It is only 0.001. Cobalt oxide, the same manner like nickel oxide, and yes, exactly like nickel oxide. The deviation is also slightly more, but not too large. 0.012. Titanium oxide is little different. One can see here titanium oxide means is to 1:1. So, X is supposed to be 1. Instead of that, the X actually varies from 0.8 to 1.3. So, it can be less than 1 or it can be more than 1 also. So, that is another situation where the non-stoichiometry changes from its middle position or the accurate position or correct ratio in both ways. Vanadium oxide is also exactly same as titanium oxide, TiO. TiO2 is different, it is supposed to be 1:2. So, only in some cases it is really 2, but otherwise it is less, it is less than 2, 1.992, which is fairly low. Cu2O 0.5 2:1 actually. So, instead of 0.5 it is 0.5016. Okay. So, basically this table means that there are large number of oxides where this particular ratio is not maintained, and normally of course it depends on the nature of preparation technique, the history, and under what condition it has been equilibrated, what kind of ambience has been maintained, whether what kind of oxygen atmosphere was there, whether it is reducing atmosphere or oxidizing atmosphere. All these things do depend, do control the exact value of x, but they have a tendency to deviate from its original ratio or ideal ratio. Well, there is a strong correlation, direct correlation between non-stoichiometry and point defect. It is quite obvious. Okay. Presence of point defect either in the cationic or anionic sublattice leads to imbalance in the ratio of the ions and thus non-stoichiometry. Okay. So, it is the point defects both in the cationic or anionic sublattice leads to imbalance in the ratio of the ions and thus the non-stoichiometry. So, non-stoichiometry is nothing but the basically the deviation from the expected ratio or the formula ratio. However, defect pairs such as Schottky pair, I have already mentioned, Frenkel or anti-Frenkel pair do not lead to non-stoichiometry, and therefore, these defects are sometimes referred to as stoichiometric defects. That is also quite understandable, because they appear in pairs. So, they do not change the particular sublattice. So, they change uniformly both the sublattices, and therefore, the ratio remains same. Different types of defects give rise to different nature of non-stoichiometry, that also briefly I mentioned. Metal excess or oxygen deficient oxides arise from the presence of defects like metal interstitials and oxygen vacancy. Okay. So, it is basically a ratio. So, if it is one is metal excess, one can also express the same thing as oxygen deficient, and once again these can arise from both the parameters like metal interstitials or oxygen vacancy. Okay. The oxide metal excess means there can be metal interstitial, additional metal ions introduced into the inside the lattice, or if oxygen vacancies have been created, also that will lead to the same effect. Similarly, metal deficient or oxygen excess, the reverse of that, oxides arises from the presence of defects like metal vacancy and oxygen interstitials. So, these are very I think it is quite common, or common sense will be good enough to understand that. Now, with this background, let us try to see whether we can write some equations, defect equations and defect reactions. Just like chemical species are denoted by certain formula, certain symbols, here also we have already mentioned that the defects have their own symbols, and they can be put together to write some chemical reactions, and depending on what kind of physical reactions actually taking place. So, we can write on papers how the reactions are taking place, which is moving where and which is reacting with what. So, just like chemical reaction, one can write reactions or defect reactions, and in the same manner we can have equilibrium constants and so on. So, defect equation and defect reactions, for writing such things we have to follow certain principles. These are some of these things are listed here. Point defects are in certain sense equivalent to chemical species, and therefore, it is possible to write chemical reactions involving different point defects, and the equilibrium constants can be expressed in terms of concentration of these defects or these species, right. Just like you can have equilibrium constant in terms of the concentration term, here also one can use the similar principle. Following rules need to be followed to write such equations. 3 or 4 things have to be remembered. Lattice, no lattice sites, okay, number of lattice sites I think. It is not known lattice sites, number of lattice sites should be, let me change it. Sorry. Number of lattice sites, the ratio of cationic to anionic sites should not be changed even after the formation of defects. As per example, 1:1 or 1:2 and 2:3, these defects, this ratio must be maintained even if some of the lattice sites are missing, but the ratio cannot be changed, because even if the a vacancy is created, the particular element may be missing from there, but the lattice site is not going to change. So, lattice site is there and we have to say that it is a vacant site. However, in maintaining this ratio, there may be changes in the total number of lattice sites. That means, the total number, whether it is 60 or 600 or 700, whatever you take, that should not change. The total number should not change, but the ratio may change. This is what is actually understood by that process. That means, you see, if you are making a vacancy here, actually the material is not there, M2 plus is supposed to be there, it is not there, but the lattice site is there, and that is the reason why we are talking about a vacancy. The other one, the lattice site is not there, okay, and that is why this is not a vacancy. This place is not a vacancy, but this is a vacancy, provided that lattice site, that ratio is required to be maintained and that site has to be considered. Defect equation and defect reaction, okay, that is what the title we are still discussing. Site creation, if a cation or anion is added to a lattice, the site for the corresponding anion or cation has to be created and to be considered as a vacant site. Okay. So, going back to that earlier diagram, let us say we have initially we have these, this was the boundary of the solid. Okay. Sorry, this is the boundary, this is the boundary of the solid. Okay. These were not there, this oxygen was not there, and we have from outside we have added that oxygen. So, we have created a lattice site, in the anion lattice site has been created. As soon as the anion lattice site is created, a cation lattice site also have to be considered, okay, because this is a 1:1. So, one you add this oxygen, this as if this lattice site is also there. We need not consider these two until unless, sorry, these two until unless another metal or oxygen has been added there. However, we have to consider this one 1:1, that means, if you have created one oxygen lattice, you have to create a metal lattice site also, but since the metal is actually not there in reality, that has to be considered as a vacancy. So, that is the reason here it was originally 16 lattice sites, now we have added one lattice site, 17th one. So, immediately you have to add 18th one also and consider it as a vacancy. So, that is the reason it says the ratio must be same, a ratio must be maintained, but the total number may change. Earlier it was 16 total lattice sites, now it is 18, that is possible, that is allowed, but the ratio has to be there. Mass balance, just like in chemical equation, mass balance also have to be maintained. In writing a defect reaction, mass balance has to be maintained on either side of the equality sign as in chemical reaction. Vacancies as well as electronic defect like electron and hole do not have any mass, vacancies do not have any mass. So, that is obvious and we have to take into account that. Charge balance, electrical charge is also to be balanced between the two sides of the equality sign. So, whenever you are trying to write a equation, just as in chemical reaction or chemical equation, we have to maintain both the mass balance as well as the charge balance, and that is really very important. Now, we will be giving you some diagrams. We may not be able to explain each and everything in details. I think they are quite self explanatory. I will consider few cases, in fact many of the possible cases. For example, we are creating an oxygen vacancy, a oxygen deficiency with oxygen vacancy, right. In fact, when you are talking about non-stoichiometric oxides and there is a correlation between non-stoichiometry and the defect. So, there is a strong correlation and equality between the non-stoichiometry and defect concentration. So, all non-stoichiometries are actually the result of creation of some defects. Okay. So, we have two types of deviations, one is oxygen deficient or oxygen excess, which is equivalent, oxygen deficiency is equivalent to metal excess, both are same basically, because we are only talking of the ratios. So, oxygen deficient or oxygen excess, or in other words metal vacancy, metal deficient or metal excess, right. So, these are the four possibilities, and all these possibilities can be again by two alternatives. A oxygen vacancy can be created by oxygen deficiency can be created either by oxygen vacancy or it can be created by metal interstitial. Both of them are actually equivalent so far as the ratio is concerned. So, here one kind of situation where oxygen vacancy is being created by oxygen vacancy. So, a oxygen vacancy, this is a lattice, perfect lattice, and then some vacancy has been created here, a oxygen vacancy has been created and two electron holes has been 2 electrons has been left there. So, a neutral defect has been created and in fact, an oxygen has coming out. This oxygen mass has come out in the form of a atom. It is atom is because it is in the coming out in the gas phase. So, we look at it as half O2, it is coming out as a molecule, but actually one atom of oxygen is coming out. So, we write it as half O2. So, that is a very common notation we use in defect equations. Here you can see this is MO and then MO plus oxygen vacancy, this oxygen vacancy plus half O2G is quite simple, that is how what is the reaction, but this is not a mass balance, this is not a mass balance. So, this is just showing what is happening. A perfect lattice is still a MO lattice is there, but along together with some defects, oxygen vacancy and releasing half oxygen. Now, this can be written in this manner: oxygen at oxygen site, we need not write the M, okay. We can just write what is happening to the oxygen sublattice, oxygen at oxygen site it was there, and that basically you are looking at this site. So, originally it was oxygen at the oxygen site, now a vacancy has been created, and together with that we have released one atom of oxygen. That oxygen has gone out from the solid to the atmosphere, and therefore, this is a simplified reaction only involving the oxygen sublattice. There is no involvement of metal in this situation. Oxygen deficiency with oxygen vacancy are the same thing. Now we are talking about a charge defect, which was earlier a neutral defect, electrons was released or left behind at that particular site where oxygen was originally there. Now that electron has become mobile, electron has become free, it is not attached to that particular site, it is not relating to that particular site, it is more mobile, and so adjoining or any two metal sites or metals has been accepted, or metal has accepted those electrons and changed its valency. So, that is how what is happening here. So, when it is we are talking about charge defects, this was the neutral defect situation, and now when you are talking about charge defects, this has been happened. Okay. There is no question of charge on this side. However, this oxygen is balancing this oxygen, and that is why this oxygen the regular oxygen, because on both sides the mass balance has to be there as well as charge balance. These are the two very important aspects of writing defect equation. So, finally, charge also has been added there. So, this has been charged, this metal vacancy oxygen vacancy which was created, originally it was a neutral defect and now it has been charged defect. So, two positive charges, effective positive charges have been created and two electrons have been released. Okay. These two electrons have been free. When we write these kind of two electrons, these electrons are free and mobile electrons. Other electrons are immobile electrons, they are strongly attached to the ion cores. So, they are not mobile. These electrons which are been created by the different defects, they are relatively mobile, and that is why it has been separately, and these electrons are actually have joined here and there. One has gone there, another has gone there. These are two electrons, that is what we write here. Okay. We do not write that this has already been accepted by the metals. So, metal is not coming here, only the electrons are coming, because these electrons may not be sticking to this particular site. We will see later on when we will see the conductivity, how the conductivity behavior of these kind of metals or non-stoichiometric oxides behave. We will find that these electrons are not attached to these two metals only. After some time they will go to that, or they are actually moving around, will be moving around from one place to another, and that is what we call the hopping of electrons. These can hop because these are free electrons. Okay. These free electrons are almost equal or equivalent to the metallic free electrons or metals, whatever we have in metals. Okay. That is why it has been written like that. Well, finally, this is the overall reaction we are writing. This is just to express what is happening, the metal oxides perfect lattice, having still perfect lattice, in addition oxygen vacancy has been created and half oxygen has gone out in the form of atom, leaving behind two electrons. Then this metal site has been removed here, and we simplify that equation like this, only oxygen just maintaining the mass balance. Here there is one oxygen and there is one oxygen here. That is why you have to maintain this oxygen. That means we are focusing on the oxygen lattice site and oxygen vacancies. So, this is of course does not have a mass, there is no charge here, all are neutral. Here a charge has been introduced and there is 2 negative charges, and then this is 2 effective positive charges, they neutralize each other, and this oxygen and this oxygen makes the mass balance. So, by that process the whole reaction can be written in the form of a very simple chemical reaction like situation, and we can also find out a equilibrium constant for this reaction. We will discuss that in the next class. Thank you for your attention.